All right, here we go. Unit 6, Lesson 10, Compound Growth, Day 2. So we're going to be working with compound growth, interest in a bank account, your car getting less valuable, all those models of exponential growth that we've been working with, and we're just going to get them a little bit more complicated today, a little bit closer to how things work in the real world. Okay, so here we go. We're going to talk about compound growth, and here's an example of what we've done so far. $6,700 is placed in an account with an annual interest rate of 8%. So every year it's worth 8% more than the year before. How much will the account be worth in 24 years to the nearest cent? So this would be a fairly straightforward one where we would take our initial amount, $6,700, we would multiply by 1 plus the growth rate as a decimal. And since the value is going up, we do 1 plus, so we do 1.08, all to the number of years. And that's a fairly straightforward one. From this point on, it's just a matter of, and I'll just kind of do this off screen here so we don't have to open up a new screen. This one's just a matter of going to your calculator of choice and typing in 6,700 times 1.08 to the 24th. And, you check your answer to make sure that it makes sense. $42,485.91. And you just check yourself, okay, if I earned 8% interest for 24 years, that's a while. Yeah, $42,000 makes sense. So that's how that one would work. We also did trickier problems where we used logs to basically set savings goals. And so, or to figure out when something would be worth some amount of money. And so in this example, a new car is purchased for $23,400. Okay, that's the starting amount. Starting amount is $23,400. And the car depreciates, right? This means goes down. That means goes down at 11.5%. So 11.5 as a decimal divided by 100, or move the decimal place 2 times, 0.115. To the nearest year, how long will it be till the value of the car is $12,700? Well, remember the way we did this is we set a goal. In this case, it's a backwards goal because we're saying basically when will the car be worth $12,700? Well, it starts as worth $23,400. And what I'm going to put here is 1 minus 0.115. 1 minus 0.115. And the reason I have to do minus 0.115, right, is because the value of the car is going down. And so what this actually works out to is that 12,700, I'm interested to know when that's equal to 23,400 times 0.885 to the power of x. And what we learned was you either have a fancy calculator that can do all sorts of logs, or you use this little trick. You divide by, well, either way you have to start this way. Either way you have to divide to find the final, like the total amount of growth or decay that you have. And so we divide 12,700 by 23,400, and we get that we want to find out when the car is only worth about 54% of what it used to be worth. And so we're basically asking the question, how many times, right? How many times do I have to multiply 0.885 by itself till it gives me a total decay of 0.543? And so what we're really asking is, and if you have a fancy calculator, you can just do 0.885, the log in base 0.885 of 0.543. What power of 0.885 is 0.543? But we learned that you couldn't always do this. Back in the day, you only had log base 10. And so the trick here is to take the log in base 10 of both sides so that you can apply our log rule. The log of 0.543 is equal to x times the log of 0.885. And so now we could divide by the log of 0.885 And either way you do it, either taking the log base 10 of 0.543 and dividing by the log of 0.885, or by just using a fancy calculator and doing the log of 0.885, you would get here that this takes, it's almost exactly, it's like 0.4, and it says to the nearest year. It ends up being 5 years. It's like 4.999. Okay, so those are what we've done so far. And here we're going to get a little bit closer to reality. And I'm going to talk to you about why it's closer to reality. This is a much more common way that growth is actually calculated. And so you put your money in a bank account, and the way we've been assuming it works is the following. If you invest $580 in an account, and it pays 4% interest, 4.6% interest, this is how we assume it's been working. Times 1.046 to the power of x to the power of 19, right? This is how we assume it's been working. And so I'll type this in off screen. We have 580 times 1.046 to the 19th. Not bad, $1,363.11. But what this assumes is that basically the bank holds your money, and at the end of every year, they give you 4.6% of it on top of your original amount. And that's called yearly compounding. This word compounding, right, means more or less, it means earning interest on interest, right? The bank pays you interest, and then your interest starts earning interest. And it starts out as not a little bit, but it grows and it grows and it grows and it grows. Or like if you're a bacteria, right, you grow by splitting in half, and then each of your parts that split in half splits in half. And there's a difference in whether or not we run that calculation, whether or not the bank hits run once a year or once a month. And so here would be how it would work if it actually ran once per month instead of once per year. So here's the trick. We're going to do the same interest rate, but with monthly compounding. And what I mean by the same interest rate, we're going to take our 4.6% and we're going to divide it by 12. So we take 4.6 and we divide it by 12, and what we get is 0.383. And what this represents is the interest per month, right? It's the amount of interest that I earn per month. It's the same thing as earning 12% per year, but it's earning 0.383% per month. Now I still need to divide this by 100 to get it as a decimal, and it's going to be a really small number. Divide it by 100, 0.00383. But again, I'm earning that every month. And so with monthly compounding, I take my 580, I multiply by 1 plus 0.00383. And now here's the tricky part. 19 years, well, I'm doing this compounding monthly, so I actually need 19 times 12. I need 228 months. 228 months. So I type all of this in, 580 times 1.00383 to the 228, and I get 1,380, I'm just going to round to the nearest dollar here, $1,387, which you'll notice is quite a bit higher, not quite a bit, it's 25 bucks, but is higher than when the bank ran that calculation every year. So the idea here is you want the bank to run this calculation as often as possible, yearly, monthly, daily, hourly. The more quickly your interest can earn interest, the faster your money's going to go up. Now, it doesn't seem like a huge difference here, but like If you have millions of dollars in the bank, right, these things make a lot of difference whether or not you compound yearly, monthly, daily. I'm just going to show one more example here, and that'll be it. So with daily compounding, so same example, right, but daily compounding means they run the calculation every day. And so I want to show you here, we can get dealing with some very small numbers. There are 365 days in a year. We'll assume it's a normal year. And so if I divide 4.6 by 365, we get 0.0126. And again, this is still a percentage. I still need to divide it by 100. So there's going to be 1, 2, 3 zeros and then a 126. But I'm going to take my 580. I'm going to multiply each day, right? Now it's every day I get to run this calculation. And so what goes here is 19 years, 228 months, and if we do 19 times 365, we get 6,935 days, 6,935. And so we work all of this out. You type this into your calculator, 580 times 1.000126 to the 6,935, and you get, once again, 1,300, and in this case, $90. So once again, a little bit higher. Now, this was not the answer they asked for, but I just wanted to use this to show the point. Yearly compounding got us 1,363, monthly compounding got us 1,387, and daily compounding got us 1,390.